Special Relativity, Length, Momentum, and Energy by J. Beck, Taylor Becerra, Alex Garcia, Mikey Gonzalez, and Madison Rain.
The speed of light is the speed limit for all matter. Imagine two spaceships traveling nearly the speed of light toward each other. Even if they are both moving at 80% of the speed of light, their relative speed would only be 98% of the speed of light, which is still less than the speed of light. There are no circumstances where the relative speeds of any material object surpass the speed of light because it is the universal limit. In order to understand why the speed of light is the universal limit, one must understand how motion through space affects the length, momentum, and energy of moving objects. Length contraction is when the object contracts relative to another object when it approaches the speed of light.
For moving objects, space and time changes. When viewed by an outside observer, objects traveling appear to contract along the direction of motion. How much an object contracts depends on the amount of time dilation, which is the stretching of time in a frame of reference moving past the observer. For everyday speeds, contraction cannot be seen because it is too small to be seen or measured. However, as an object approaches the speed of light, contraction is more noticeable. For example, if a meter stick was to move at 87% of the speed of light, it would appear to only be 50 centimeters long. The crazy thing about this is that both observers would view themselves as normal and the other object as contracting, even if only one of them is moving. The contraction of speeding objects is the contraction of space itself. Space only contracts in one direction, the direction of motion. As relative speed increases, contraction in the direction of motion increases. Lengths in the perpendicular direction do not change. As shown by the image of the baseball, when the velocity of an object is equal to 0, the object's measured length while in motion is 100% of the measured length of the object at rest. When the object is sped up to 87% of the speed of light, though, its measured length while in motion is 50% of the measured length while the object is at rest. The object will continue to shorten in length until it reaches the speed of light, upon which theoretically it would have a length of 0% of its measured length while at rest. The length contracting formula is represented by the L, the length of the moving object, which is set equal to the measured length of the object at rest, times the root of 1 minus the speed of the object squared, divided by the speed of light squared. With this formula, you are able to prove that the speed of light is the universal speed limit for the universe. If you were to approach the speed of light, your observed measured length is going to become shorter and shorter. But when you become equal to the speed of light and input the speed of light into the equation, you will find that L becomes equal to 0, which is impossible due to the fact that you cannot lose or gain mass. This proves that no object can travel at speeds equal to or greater than the speed of light.
If you were to continually push on an object that was free to move, it would continue to accelerate. It seems that if you continue to pushing it, it would increase with that limit. However, the speed limit of the universe is the speed of light. In order to understand this, you need to understand Newton's second law, which states that force equals mass times acceleration. You also need to know that momentum equals mass times the velocity of an object. According to those equations, momentum can increase without limit. However, for special relativity, Einstein showed that momentum's formula can be changed to P equals mass times velocity over root 1 minus v squared over c squared, where v is the speed of an object and c is the speed of light. This equation is similar to time dilation's formula. It tells us that the relativistic momentum, which is momentum at high speeds approaching the speed of light of an object, is larger than mass times velocity by a factor of 1 over the root of 1 minus v squared over c squared. As the velocity approaches the speed of light, the denominator of this equation nears 0, which means that momentum approaches infinity. However, this is impossible because it would require an infinite impulse. When an object's velocity is much less than c, the denominator of the equation is close to 1 and is nearly equal to mass times velocity. A particle pushed close to the speed of light acts as if its mass were increasing because its momentum increases more than the speed increases. This is called the rest mass of an object, which is independent of speed and energy. This is a true constant and it will never change, no matter how fast an object is moving.
Momentum of a high-speed particle can be described in terms of the stiffness of its trajectory. The more momentum an object has, the stiffer the trajectory. In the picture, an electron beam is directed through an electromagnetic field. The dotted line shows the path of the beam if it was equal to mass times velocity in Einstein's equation of momentum. The solid line shows the path of the beam if it was greater than mass times velocity, which is stiffer than the dotted line.
Einstein's special theory of relativity is that a piece of matter, even if at rest and even if not interacting with anything else, has energy of being, which is called rest energy. He concluded that it takes energy to make mass and that energy is released when mass disappears, which is kind of like a potential energy. The amount of rest energy, E, is related to the mass, m, by this equation E equals mc squared, where c is the speed of light. In ordinary units of measurement, the speed of light, c, is a large quantity, but its square is even larger. It is a ratio of rest energy to mass, E divided by m equals c squared, which the magnitude of c squared is 90 quadrillion, which is 9 times 10 to the 16th power joules per kilogram. This equation is not restricted to chemical and nuclear reactions. It is much more than a formula for the conversion of rest mass into other kinds of energy, or vice versa. It states that energy and mass are the same thing, and mass is just simply a congealed energy.
The formula for total energy of a moving piece of matter is E equals mc squared over the square root of 1 minus v squared divided by c squared. The only difference between the two formulas is that the kinetic subtracts the mc squared at the end, where the total mass formula doesn't include the subtraction of mc squared. The kinetic energy formula is Ke is equal to mc squared over the square root of 1 minus v squared divided by c squared minus c squared. Another difference is the total matter formula also accounts for matter at rest. When an object approaches the speed of light, the momentum and energy do so as well, so there's no way that the speed of light can be reached.
Important things that you should take away from this video are, first of all, the speed of light is the speed limit of the universe. Second of all, as an object approaches the speed of light, the more it will contract. Third of all, the greater the momentum an object has, the more resistance it has to outside gravitational force. Finally, and most importantly, with Einstein's formula of energy equals mass times the speed of light squared, we are able to reach the conclusion that mass and energy are the same, except mass is simply just a congealed energy. Thank you and have a nice day.